Okay, so as I said, we are interested in some point, get some point on the card to trace that curve. And so what we'll do is, for the manipulator, it was the end effector, right? Here we'll just put some random point on the robot. I'll call that P. Okay, and P will have a general position. I'll call that, it'll be a distance of Px, Py from the center, but then you can change the point P to be whatever you want it to be later on. So let's say that this distance is, that's along the y-axis, so that's Py, and this distance is Px. So that's the distance from point C. And when this car has turned, this point clearly has to be at the same distance when you see with respect to the frame 1, right? Because that point is not going to change its location on the chassis. It's going to be same Px, Py, but its location in the world frame will be different. So let me call this xp1. So this is point P. Let's call it xp. I can erase this. Yeah, and if you want, you can call this xp0, yp0. Okay, so our goal here get the point P to track a given reference trajectory. Okay, let's just call that x ref as a function of time, y ref as a function of time. Okay, so if you want to do that, then we need to write an expression for the position of point P in frame 0, right? Because this path is going to be in world frame. So what I'm going to do is, I'm going to try to relate xp1 with xc1 and xp1, and then we'll go from there. So from the figure, we can see that we can write the position of C0 in frame 0 as R10 times C1. Okay, so that's not new. That's basically saying how C0 is related to C1. We can also write position of P0 as R10 P1. Okay, so there is also a translation component to it. And O P10, it's going to be the same. But the point is, you don't really need to write that, because what I'm going to do is I'm going to take the difference. So that'll actually drop out. So if I take the difference, C0 minus P0, or let me do it, P0 minus C0 actually. Okay, so I'm subtracting this minus this. So we'll get R10 P1 C1. So that D basically drops off. It doesn't really matter. Okay, so let's just expand this out. What is P? It's basically has a x and y position, and R is basically cosine, sine, that formula. So let me write it down that way. X P. Yeah, sure, yeah. Yeah, no problem. XP0 minus YC0 equals, this is the expansion for cosine R10, so cosine theta minus sine theta, sine theta, cosine theta, and then there's going to be xp1 minus xc1, yp1 minus yc1. Okay, but note that this part, which is the position of point P in frame 1, remember the frame 1 is the one which moves with the car. So that point P is going to be always the same distance from point C. So xp1 minus xc1 is nothing but px, and xc1 yp1 minus yc1 will be py. That's not going to change, so I'm going to just sub that in. So cosine theta minus sine theta, cosine theta, and this thing here is px py. Okay, so we can write, well, and this we'll be needing this. We'll write two formulas. One formula is if a given position of C, we can write position of P. If a given position of P, we can write position of C. So given position of P, we can compute the position of C. Okay, here I'm just solving for xc0, yc0, assuming that I know xp0, yp0. So in that case, it'll be xp0 minus cosine sine we can also do the other way around. Given the position of C0, compute P0. So this is only needed for our animation a little bit later. So I'm just writing it down here. So we're just trying to solve for xp0, y0 given this. We just have to move the thing on the right-hand side the other way. So xp0, yp0 come from the first previous expression is xc, yc0 plus cosine theta minus sine theta, sine theta, cosine theta, px, py. I just put a note here, needed for IK code later. Okay, that's fine, but remember we don't have access to xp, xc and yc because the equations of a car are written in terms of velocity. So we'll differentiate with respect to time. So the top expression, so we can compute x dot p, y dot p equals x dot c, y dot c plus. So when you want to do the derivative of a rotation matrix, remember that px, py is a constant. So it's only the part in the matrix. All you've got to do is differentiate each element with respect to time. So the derivative of cosine theta is negative sine theta. And then I need to take the derivative by chain rule, take the derivative of theta. That'll be theta dot. So that will be my row 1, column 1. Then derivative of sine theta, which is cosine theta. Then you take the derivative of theta because by chain rule. And then I can keep doing that. So sine is cosine theta, theta dot, and cosine is minus sine theta, theta dot. And remember, px, py is a constant, so I don't need to do anything with that. Just keep it as it is. If you think this is hard, what you can actually do is you can write that as two equations. The first line is the first equation. Second equation, differentiate with respect to time, and you'll get the same expression, the one I wrote down here. Okay, so what I'm going to do is just make some modifications to this expression, x dot p, y dot p. Remember, we know what x dot c is. We derived that expression earlier. It's right here, right? X dot c is v cosine, y dot c is v sine. So I'm going to sub that in. V cosine theta, v sine theta plus, I'm just going to go ahead and carry out that multiplication. So that would be minus px sine theta, this way, minus sine theta px theta dot minus cosine theta, theta dot, or rather py theta dot, and cosine theta px theta dot minus sine theta py. Yeah, I'll just simplify the whole thing. I'll just combine those two things and write one formula for xp, yp. Okay. Right, rewriting the same thing, just simplifying it. So it's v cosine theta. And I'm going to make a change here. Remember that theta dot is omega, right? It came from, I think it's this expression. Theta dot is omega. I'm just going to sub that in. So if I do that and expand this, I get v cosine minus px sine theta minus py cosine theta times omega, and v sine theta plus px cosine theta minus py sine theta omega. Okay, now really what I want to do is I want to be able to write solve for v omega. So I'll just one last step, and this will be it. This is the final thing before we can use it. So cosine theta sine theta, I'm going to write it as a 2 by 2 matrix times v omega. So I just need to pluck out v and omega. So that will be minus px sine theta minus py cosine theta, and then px cosine theta minus py sine theta. Okay, so this is my final expression for the rate of change of velocity of the point P, and the point P is the one which I'm interested in tracking a curve. Okay, so now the way I'm going to make this track the curve is, and this is I'm giving you how to do it, but why it works, we'll come back to it later when we talk about controlling simple systems like a pendulum. So what we need to do is we need to set x dot p as a gain, let's call that kpx, times x ref of t minus x p0, and y dot p0 is kpy y ref t minus yp0. So these two things are sensor measurements. You need to be able to track the position of P. So if you want to track the position of P on or any point on the chassis, you probably need some external vision system to track the position of P. And so this is basically a controller to track x ref t, y ref t. Okay, as I said, we'll come to the theory when we talk about controlling the pendulum. Don't worry about it right now. So what we'll do here is we'll put these inside this expression. So let's call this, let's say 1. kp x x ref minus xp0 kpy y ref minus yp0 equals cosine theta sine theta, an extra theta here, minus px sine theta minus py cosine theta, px cosine theta minus py sine of theta. Okay, if you think of this as B and this as A, and this thing here is unknown, then you can solve for x as A inverse B. Okay, x basically is the speed v and omega which you're trying to control. Now it turns out for this 2x2 matrix, this inverse is easy to compute. You don't really need to do it numerically. You can do it symbolically. So I just have the expression for A inverse here. A inverse is actually cosine theta minus py divided by px sine theta, then sine theta plus py divided by px cosine theta. That's line number 1, or row 1, and then row 2 is minus 1 divided by px sine theta and 1 divided by px cosine theta. So all you need is that A inverse, and then of course you need the reference trajectory. Okay, so what I'll do is I'll show how this is used to track not a circle. Circle is pretty easy to track with a differential drive car. You don't really need to do all this. All you need to do is set a V and set an omega, and then you'll see that for a given V omega, it actually starts moving in a circle, right? If the car is V omega is 0, it goes straight. But now if you move the one of the wheels slightly faster than the other one, it starts slowly turning. So the circle is kind of embedded in a differential drive car. It's very easy to do that. Let's do a different curve. Let's do an asteroid. Asteroid is, which actually looks like this. Asteroid. Looks something like this. The equations, which is what we want, are in that 50 curves I gave you. X ref of t is cosine cube pi t divided by 5, and y ref of t is sine cube pi t divided by 5. Okay, so let's see if we can get the car to track that curve. Do you see the animation now? Let me keep this on. Okay, perfect. Okay, so to recap, the code basically is set so that it does animation, it does computation of the control, and so on. So I just went through parameters first. These are the parameters set. Kp is basically the a gain, which basically was one of the questions. It's user chosen. I just chose 10. Point P to C is basically given point P. I can compute the location of C. This is one of the equations I wrote down. I'll need it repeatedly in this code. Given the position of C, I can compute the position of P, again, something which I wrote down in the notes. Animation is basically standard stuff I've done in this course using patches, not patches, sorry, just drawing lines and shapes. You could use patches. And then Euler integration comes from the previous class where I did Euler integration in order to do the forward kinematics. So what this code does is, and I've tried to comment it out, for the given reference motion, I compute the position of C, compute the position of P, and this is where the point C to P, those functions help. I compute the error. Error is basically the reference, the points on the asteroid minus what actual position is followed by the point P. Okay, and I get P because I can use this thing over here, the function from C to P. I wrote down B tilde. This is the same as B in the notes. So what is B? The reason I wrote B tilde is because I think I used B for the width of the half width of the car. So I shouldn't use B in my notes. So I'd use B tilde. It basically tells you Kp times the error in X, error in Y. Here Kpx is Kp, Kpy is Kp. I just chose the same, but you could choose something else. And then A inverse is that inverse I wrote in the notes. That gives me that times B. A inverse times B gives me U. Now U is basically a 2x1 matrix. First entry is the velocity, second entry is angular speed. And once I get that, I can stick it in the Euler integration. And that will basically give me the rest of the stuff, trajectory and path.